waking up early. So this talk will be based on a program I've been pursuing in several years in these particular papers, starting with work with Witten a couple of years ago. Then the B model version is in this paper from past year. And in the end, if I have time, I'll tell you a little bit about geometric representation theory related to Teichmüller theory, which is based on work in progress with my ex-student, Tudor Dimofte. But since this is morning talk, let's have some fun, and fun may mean different things. So this is how some people view what makes a mathematics problem fun. But a more serious answer comes from, for example, from this interview with Sir Michael, who after being asked the question, what is fun in mathematics, says that the main thing that interests me in mathematics is always the interconnection between different parts of mathematics. The fact that one single problem can be approached in many different ways, a bit of algebra, a bit of geometry, a bit of topology. And today, just like in the whole theme of this conference, we'll see a nice mixture of different subjects. So in fact, my goal will be to kind of illustrate this phenomenon, which again is very universal, and we'll see it throughout this whole week. We'll talk about one subject. I'll start with the representation theory. Then I'll completely switch gears, and we'll talk about something which a priori looks completely different. And half of the way through the talk, we'll be able to see the connection. So we'll see that we're actually talking about the same thing, even though it won't be apparent from the very beginning. So this is basically what I just said, and with a little bit more detail, we'll be talking about representation theory on one hand, symplectic geometry on the other hand, and in the end, again, if time permits, we'll talk a little bit about application to quantum groups and low-dimensional topology. So we'll have a little glimpse of application to three-manifold invariance and not invariance. The general phenomenon that I want to illustrate on this talk, and again, it's a relatively short lecture, and you could have a whole course devoted to branes and geometric representation theory, but the phenomenon that we'll see is the following. We'll start with a physical system, or I won't present it in this way, but conceptually that's where representation or geometric representation theory comes from. One can start with a physical system which has a symmetry group. And then, essentially, by definition, anything that you can see in gauge theory will inherit this symmetry. So that's the key principle. In particular, in physics, we're often interested in various moduli spaces, and this is not new. What is new is that we'll be looking at D-branes, thinking about this moduli space as a target space, essentially. And then, because, again, everything has inherent G action, the problem will produce for us the whole plethora of representations related to that symmetry. So that's the basic principle. That's how, in physics, representations of various groups, various symmetries, may come from geometry, and there is a very natural way to do it, essentially by reproducing these moduli spaces as supersymmetric vacua or something else. So this approach is not new, as the long list on the right side indicates. And of course, it starts with basic BWB theorem, which realizes finite dimensional representations. And here I organized the list, essentially listing some of the, by far not all, but some of the works approaching this problem from the symplectic side, where you start with moduli space. They don't call it like that. They just say we start with a space. And think of it as a symplectic manifold. For example, orbit method is one way where you can construct representations from geometry. And we'll be able to see how it can be embedded in this slightly bigger framework. Then here I list another much more powerful approach. So symplectic approach, followed by many people. Again, it's typically some version of the orbit method, basically. Unfortunately, it misses some ingredients. For example, and I'll be able to illustrate this in a talk, if you want to construct even representations of the basic example, say group SL2R, which will be our toy model for this talk, it won't work in general. So there'll be some pieces in geometry which are missing. For example, the ones corresponding to the complementary series. I'll get back to it. And therefore, this is a very nice visual approach. It's very geometry-based. Everything is good about it. But again, there are some ingredients missing. Then there is a complementary point of view. So in mathematics, there is not even a single school, but many generations of people working on similar problems or related class of problems where they're trying to understand representation theory from the point of view of geometry, but mostly using the language and tools of algebraic geometry. This is way more powerful. In particular, there is nothing missing. Nothing. They can get every single representation, but unfortunately, it's not entirely visual. Algebraic geometry, as powerful as it is, can crash through any problem, but sometimes it makes it hard to see particular representation or what exactly you're doing. In fact, if you ask a single question, something like, which representations are unitary? It's very easy to see in this approach. It's essentially built in, and again, it's based on the fact that everything is very visual, very simple. In language of algebraic geometry, this becomes a hard question. So this is not so easy to answer from the viewpoint of algebraic geometry. So therefore, what you can ask, what is that I can offer to this long history of research? And the way my friend Edward Frankel would put it, he would probably say that branes, they're kind of hybrids of both. On the one hand, we'll be talking about A-branes and Lagrangian branes. Therefore, they're submanifolds. They have geometry associated to it, and they belong to the symplectic part. So it feels like they're close cousins of these fellows. However, promoting Lagrangian submanifolds to branes brings something new. In particular, it fills all the gaps that you would have in this program and shares a little bit with algebraic approach. So by the fact that D-branes are, essentially you can think of D-branes as quantum version of Lagrangian submanifolds. So this is where we'll be able to buy some extra mileage. This is where, for example, you can find complementary series representations of SL2, fill some gaps from here, but in the same time, you'll retain control of what's unitary, what's not, and so on and so forth. So branes will offer kind of hybrid and complementary version of either one of this. OK, so without further ado, I'll just go to my first subject. And as I say, I'll present first representation theory side, and then we'll switch gears and talk a little bit about symplectic geometry. Well, let's talk about representation theory of the simplest group. I don't want to deal with SU2 because that's way too simple. And again, we don't need much new technique. And even though we would learn about branes, even with SU2, it's more fun to start with SL2R. These are the standard generators of SL2R. They're commutation relations. And of course, it's very important to introduce the central element, which commutes with everything in terms of the standard triple H, F, and E. Omega, which is my Casimir operator, has the following form, H squared plus 1 plus this symmetrized combination of E and F. Our goal will be to study representations and ultimately unitary representations of SL2R. And important point which I want to note is that, well, first some definitions. Let KR be the maximal compact subgroup. And GR in general will be some real group. R indicates that it could be a real form of something complex or just real on its own right. And in the present case of SL2R, of course, the maximal compact is SO2, just the group of circle rotations. Then we'll be interested in representations. We'll call them pi. Pi and V. Pi is denotes how the group acts, and V is the vector space on which it acts. We'll consider representations of the Lie algebra of the big GR of the group, but such representations which are compatible with an action of the maximal compact. So therefore, what we'll be talking about in mathematics language is representations for G and K together. These are sometimes called Harishchandra modules or admissible representations. And at some point, we'll allow ourselves to analytically continue everything. So in fact, later on, loosely speaking, we'll actually be talking about representations of Lie algebra of G and Lie algebra of K with a compatible action. But for the start, let's just consider the canonical usual definition. We'll be thinking of pi and v equipped with an action of G and also with a compatible action of the maximal compact. What does it mean for our particular example? Well, it means that v can be decomposed in the sum Vn, where n denotes essentially the weight of the SO2 action. And the story has a more general version, of course. If your group GR is a real form or real group, such as SL3R, SL4R, or it could be a real form of G2 or some other exceptional group, there is always maximal compact. And you can ask about decomposition of your representation space into reducible modules with respect to this KR action. In the present case, again, KR is just a circle group of rotation. So V can be decomposed in the direct sum of components, each labeled by what's called K-type. This little n is what's referred to K or KR type, and it basically is the weight of how the circle acts. By definition, we'll say that a vector belongs to space Vn if this holds. OK. Now, this was essentially a definition, in fact, a standard one. And then pursuing this a little bit further, in case of SL2R, you quickly conclude that these types, K types, take values in mu plus 2z. So mu is some fixed number, could be complex a priori. But then all of the, for a given representation, all of the K types, all of these eigenvalues for the circle action have a spacing which in my normalization is equal to 2. So therefore, for example, raising operator changes the eigenvalue, the K type, by plus 2. Lowering operator changes the K type by minus 2. So you have, if you start with a given eigenvalue, say, let's call it mu, you'll be going through a bunch of points on both sides of the mu, in positive and negative directions, so to say. So you'll have the whole chain of eigenvalues of equidistantly spaced points with an offset, specific offset equal to mu. Of course, mu is essentially defined up to 2, modulo 2, because of this. It just says how I'm offsetting these numbers.
Why is it not just integral? I mean, I thought you were labeling the weights by the, just the eigenspace of the SO2.
Right. So here I want to, at the level of algebra, everything is consistent if at no point in the previous slide n had to be integer. So I called it n, but the algebra, the way how the Lie algebra of GR acts and how the compact group KR acts, does not require n to be integer on the previous slide. My notation was very suggestive, but yeah. Here we go. So
you're representing the Lie algebra of K or actually the group K?
For
KR, GR, KR.
Yeah, for that's why I made this careful remark in the beginning. Actually, in the end, we'll be representing both Lie algebra of G and Lie algebra of K. In good situations, for example, for nice unitary representations, we'll require that action of the Lie algebra integrates to the action of the group. But it's
You've got cos theta there, right?
Yes.
So the right-hand side is the invariant to the n in 2 pi. So n has to be an integer.
Well, that's when you represent.
That's when you represent the group, right? So as I say in the beginning, let's relax this a little bit. So in that case, OK, so if you wish, it doesn't matter in which stage we're going to relax this condition. But for good unitary representations, n will be an integer. But as I say, later on, it will be useful to relax this a little bit and consider not just G capital K modules, but lowercase g and k modules. So it's a very good idea. And again, it doesn't matter. I can do it later. You'll see why.
I don't understand what the difference between the GK module and the G module.
In that case, It's very subtle. So again, let's relegate this till the very end or following discussion, because GK module, where K is not the group, but rather just a Lie algebra, is analytic continuation, and I have to tell you in what sense. So unfortunately, this requires a little bit more time and work, but believe me, it's all consistent. So one point I want to draw your attention to is, indeed, this formula works and gives a nice definition for GK modules where K is the group, maximal compact, then indeed n as the integer, and you get the usual story. But as I say, it's very useful to allow yourself do analytic continuation later on, and I'll show some aspects of it, but probably not in great detail. But we'll come back to it. That's a very useful point. So thank you very much for paying attention. So thanks a lot for noticing this. These are very important, relevant details, but probably a little bit too technical for the first two slides, or someone who hasn't seen representations of a SL2R. So I believe there are people in the audience coming from, say, symplectic side, for whom this maybe even the definition of K-types is fairly novel. So for me, in the most general context, let mu be a complex number. Again, we'll talk about analytic continuation later, and it's a good idea. So we prepare ourselves to this generalization. Of course, it's defined modulo 2, essentially because it labels the offset of how this index n differs from the integer. And again, it doesn't matter where exactly we start the counting. And in the math literature, it's often called lowest K-type. I'll explain this in one example. Sometimes it will actually be the highest K-type, but in the literature, usually mathematicians still use the definition where it's called lowest for some reason. OK. Now, one important ingredient in this formula is that the omega doesn't change the K-type. So if you act on a vector coming from eigenspace of that decomposition with weight n, you'll stay with that same eigenspace. And in fact, you'll find the same vector because omega is central. All you can get is multiplicative factor. But that multiplicative factor is very important. It's essentially the value of the Casimir. And we'll call it lambda, or in this normalization, lambda squared. And then we just discussed in more detail the second ingredient. We'll call it mu, the offset, or this lowest K-type. So far, just by starting with the definition and trying to ask for compatible actions of the Lie algebra of G, some real group, and its maximal compact subgroup, we're, and running through some of the algebraic details, we're concluding that there is a possibility of two complex numbers, or Paul wants mu to be integer for the start, in that case, complex number and an integer, perhaps, which label possible representations. And this is indeed correct. In general, what we just described is essentially the definition of admissible representations, or equivalently, Harish-Chandra modules. And they're essentially labeled exactly by these two pieces of data. One piece of data tells you how maximal compact acts, and there is this offset which we call mu, the lowest K-type, or sometimes it will be the highest K-type, plus the value of the Casimir. And at least for SL2R, all representations, all Harish-Chandra modules, will be labeled by these two ingredients, by these two pieces of data. And now let's come back to our crash course on SL2R. There are several types of unitary representations. Here in this discussion, and as I insisted, I wanted to make mu and lambda as general as they can be. So for SL2R, this would be even complex numbers if I allow myself to do this analytic continuations. Now I want to go back to the canonical standard theory and ask, in this big soup of representations, as we discussed, sometimes they are not even representations of the group. They're only representations of the Lie algebra. And surely they're not going to be unitary, most of them. So now we can ask the question, which of those fellows, for which special values of complex mu and lambda, will find something unitary? OK, so now we go back from the more general story to the less general but useful story with unitary representations. The notion of lowest k-type is perhaps easier to explain by the example of a discrete series representation. These representations are labeled by integer n. And they correspond to specialization of some of this central character in the k-type to the following values. Lambda is essentially n, and mu is n plus the sine of n. There are sometimes different ways of labeling discrete series representations. Sometimes people talk about dn plus and dn minus, where n is positive. Sometimes, like I do on this slide, people talk about dn allowing n to be positive and negative, but then you don't have to worry about plus and minus. One interesting point, which you do have to remember in both cases, no matter how you label representations, is that for n equals 0, something interesting happens. There are essentially two representations which have label 0, and sometimes they're called limit of discrete series representations. So to emphasize that there are two of them, for n equals 0, I'll restore this superscript plus or minus. Okay. And this is how they look like. Correspondingly for positive and negative values of n. So this graph represents the plane of weights of k-types. Basically, this is the mu plane from our previous discussion. And it shows how the action of the compact, either group or Lie algebra, is represented. So each dot or each little box here represents the k-type or eigenvalue. So the feature of these discrete series representations, either of them, is that you can start with a particular point which will be lowest k-type, and in this case the definition or the nomenclature lower really makes sense. You start with this particular vector, and then you can act only by increasing the k-types. If you try to go the other direction, you'll find that the lowering operator, the one which would lower the k-type, would actually annihilate this vector. So this is a rather special condition, that lowering operator would kill this particular vector. And that's why for this series of representations, what happens is that mu and lambda get locked. So mu essentially has to be equal to lambda in order for this to happen. Up to plus or minus 1, up to small correction, there is a relation between mu and lambda, so they are no longer independent. And in principle, if you want to try to start with the discrete series representations which are unitary and perform analytic continuation, as indicated in this picture here, what you can do, you can promote lambda to be a complex number, but mu, the k-type, has to follow this guy. Because there is this condition that for the lowering, acting with the lowering operator in this particular vector should give you 0. Otherwise, it wouldn't be the lowest weight module. And this is analogous highest weight module, where there is analogous highest weight vector, and you cannot continue any further. So this is fairly standard story and justifies notation for lowest and highest k-types. Now, in this respect, principal series representation is perhaps the least interesting, because in some sense it's the most general, especially if you start with this analytic continuation to the Lie algebra action. It is essentially the most general representation that you can have. By allowing lambda and mu to be complex, you can construct this representation of the Lie algebra, and the k-types, again represented by these dots here, will run indefinitely in both directions. So they'll never stop. They'll never terminate at no point. Some useful facts from representation theory is that, again, if you want to ask which ones are unitary, the fact is that when lambda is pure imaginary, they'll be unitary. And in this case, the k-type does have to be an integer. So sometimes they're labeled by real variable s, which is the imaginary direction in the lambda plane. Another useful fact is that representations obtained by switching the sign of s, or equivalently by switching the sign of lambda, are equivalent representations. That's another useful fact. And finally, we see connection to this discrete limit discrete series representations d0 plus and d0 minus by adjusting the weight lambda, the central character lambda of principal series representation p plus and p minus. to 0, you see that one of these guys is irreducible. So you still have a nice irreducible representation even at lambda equals 0. But for p minus, which corresponds to a different choice of the k type here, you see that it actually becomes reducible and splits into this semi-infinite rays of k dots, as if I can loosely call it that, going in to the left and to the right, and therefore the whole representation of Fessel-Tor becomes reducible. Okay. Now, from algebraic viewpoint, the complementary series representation, which I'll call C, is just an analytic continuation of the principal series to the real values of lambda. So you have this cross where lambda was on imaginary ray, and that was describing unitary principal series representations. Now, if you try to continue to the real axis, if you want to maintain unitarity, you won't be able to continue it very far, but at least you can continue it within the interval bounded by plus minus 1. So that would be fine. And just like a principal series representation had some equivalence obtained by inverting the sign of lambda, the same property continues to hold for complementary series representation. So again, if you haven't seen much of these details before, think of complementary series as just analytic continuation of the principal, unitary principal series to real values of lambda. And for us, this is, if you wish, justification of why thinking about analytic continuation may be useful in the future. So now we want to switch gears and present a different part of the story, which will be very much in the spirit of proofs by ancient Greeks. When, if they wanted to prove a statement, they would basically show you the pictures for both sides of the statement in such a way that it makes the relation completely obvious. So they would basically show you the pictures and say, see. So this is what I want to do next. I'll start with a very different problem coming from symplectic geometry. And let's talk about symplectic geometry of four manifolds. We'll be studying two-dimensional surfaces in a four-dimensional space. And we'll ask the following question. When a two-dimensional surface can be knotted? When can you have non-trivial knottedness? And we have to equip surfaces with a little bit of structure in order to make the problem interesting. Because if you don't put any structure, any surface can be essentially unknotted. There is not much there. But you can get a little bit of mileage and make the story a little bit more interesting if you ask for surfaces to be Lagrangian with respect to a symplectic structure on a four manifold. So we'll be working with a class of problems where you have symplectic four manifold and embedded Lagrangian in there. And then we'll be asking what are the non-trivial properties or topological types or knottedness that we can observe. First statement that's due to Eliashberg and Polterovich is that all Lagrangian cylinders and planes are unknotted. So you cannot have any interesting knottedness if the manifold is just homomorphic to a plane. However, you can have interesting knottedness if Lagrangian is a torus. And in fact, a compact Lagrangian surface can be knotted in this sense only if and only if it is a torus. In fact, example of such Lagrangian torus or knotted problem was constructed by Chekhanov not so long ago, relatively recently in 1993. So he found examples of Lagrangian tori embedded in the simplest symplectic manifold, in this case just R4. So let's start with R4 as our basic example. He found examples of tori which are embedded in R4 but are not Hamiltonian isotopic to the standard torus. So you can think of usual torus sitting inside R4, and we'll talk a little bit about that in a second. And he found other examples by studying foliations, and this is what this picture is supposed to illustrate. So, of course, this problem becomes way more interesting when you proceed from R4 to more interesting symplectic manifolds, and we'll consider a little bit of such generalizations. But even with the basic example, which I'm going to explain to you in detail, based on R4 and its slight generalization, we can have a lot of fun. And in fact, believe it or not, we'll rediscover this classification of representations of SL2R. So let's start with R4, and I'll call this space Y, and I'll put two complex variables. I'll equip it with two complex coordinates, W1, W2. In that case, it's very easy to embed a torus, two-dimensional torus in this symplectic manifold. I won't specify with respect to which symplectic structure, but it's easy to work out, by simply requiring that absolute value of W1 and W2 is equal to 1. So clearly, this is a product of two circles and gives you what should be a standard torus in R4. And it is Lagrange. One useful property of this torus, which will be useful to us later, is that it bounds two holomorphic disks in this four-dimensional space. When you think about knottedness and which manifolds are related to each other and which are not, it's very useful to resort to Gromov's theorem and think how many non-trivial holomorphic disks can be bounded by this Lagrangian. In this case, there are obviously two, and here are explicit formulas, the examples, and it's actually very easy to see from the definition. In one case, you keep W1, for example, equal to 1, and look at the disk where W2 is less than or equal to 1 in absolute value, and the same with planes 1 and 2 interchanged. So in usual notations, if you have A and B cycles on the two torus, of course, these disks are simply bounded by corresponding A and B cycles. Okay. The second useful fact about this torus is that it's actually invariant under SO2 action, which acts by rotation with opposite phases of W1 and W2. So I'll call this SO2 action KR, anticipating connection with SL2R and classification of representations where this will be related to action of the maximal compact. Okay, so this circle action on the full space Y, which for us is R4, is actually Hamiltonian, and the moment map of this space is what I'll call X3 on later slides, and it's simply the difference of absolute values of W1 and W2, as very easy to see from the definition. Since the weights are plus minus 1, you have plus 1 here and minus 1 here in the contribution to the moment map. But then what we can do is the following. What we really have here is example of a problem where we have symplectic manifold with a Hamiltonian circle action, and Lagrangian is actually invariant with respect to the circle action. So what shall we do? Obviously, we shall reduce the problem to lower dimensional context by doing symplectic reduction. So that's what we're going to do next. This cries out for symplectic reduction, where we start with a space Y, which was a R4 in our basic example, and look at the symplectic leaves with a fixed value of the moment map. And again, anticipating connection with the SL2R, I'll ask this value to be lambda. And then just by dimensional analysis, you can easily see that what you're supposed to get is a two-dimensional plane. We start with a four-dimensional symplectic space. We perform symplectic reduction with respect to circle action. So we have to get a symplectic manifold in 2 dimensions lower. And surely this is just a two-dimensional plane, or if you wish, a complex plane illustrated by this picture. I'll parameterize this complex plane by x1 plus ix2, which is product of w1, w2. The combination, which is not set to a fixed value by the moment map condition, that was what we used to call x3, and that has to be fixed in the symplectic reduction. If you wish, these are 2 other moment maps thinking about the circle action with respect to hyperkähler structure on R4. Now, in this reduction, what happens? We start with the Lagrangian manifold, which is invariant under circle action, and therefore it has to descend to a Lagrangian submanifold in a symplectic space after the reduction. So here in this plane, there is a special point where the circle action degenerates, which corresponds to degeneration of the circle action in R4. This is origin in the original symplectic space R4. It projects to a point in this 2-dimensional plane after symplectic reduction, and Lagrangian submanifolds will project to various 1-dimensional Lagrangian submanifolds in R2. again, on dimensional grounds. In this problem, every line or every one-dimensional subspace in R2 obviously is Lagrangian. So in 2 dimensions, this condition is not very restrictive. But one interesting property which this figure illustrates is that this Lagrangian submanifolds may, in fact, end at a special point where circle action had a fixed point. Now, it's very easy for me to explain the difference between 2 knotted tori which have different type of knottedness according to Chekhanov. One of the tori, which is what we in real life would call usual torus, or more correctly, it's called split monotone torus, that we just described before in Gore details, and which has 2 holomorphic disks in there, represented by one-dimensional line in this symplectic reduction that surrounds this critical point, the fixed point of the circle action. And indeed, think about this. We have already one circle here, but this is supposed to represent the symplectic reduction. So there is also a circle in the fiber, and you essentially have S1 fibered over this one-dimensional line, so you do get a torus. Just like in this picture here, except that on the right-hand side, this is a different torus. And what Chekhanov says is that these 2 tori are not related by symplectomorphisms, are not related by Hamiltonian isotopies. So what this picture illustrates, you can wiggle this torus or this one, this curve and 2-dimensional symplectic space as much as you want, but you're not allowed to pass through the special point, which was a fixed point of the circle action. And again, if you take this picture and lift it to R4, you'll produce this special Chekhanov's exotic torus. Okay, now let's go back to representations, and we'll repeat the same story, except we're going to replace R4 with a symplectic manifold T star of CP1. You can view this as a hyperkähler reduction of H2 by S1, or equivalently as a quadric in a 3-dimensional complex space. Okay, so this has many different incarnations, many different names, but this will be our replacement space Y, replacing R4. It is a hyperkähler space, and much of the story that we were describing before has its version here. So this is the metric, hyperkähler metric, written in the what physicists know as Iguchi-Hansen form. It's written in terms of harmonic functions, which has 2 poles, 2 special points, which are exactly the points where a circle sitting on top of this 3-dimensional space would degenerate, and physicists usually call these points Taub-Knut centers for whatever reason. This is the explicit form of 3 symplectic forms written in terms of x's, coordinates on the base, and chi, which is coordinate in the fiber. And now let's ask the same question as before. We'll be looking at Lagrangian submanifolds in this space invariant with respect to a circle action, where a circle is just rotation along the fiber. Now, you can pick any symplectic form out of this triple, because you see they're all symmetric anyway. There is a democracy here. And because of the structure, what it means is that with respect to this 3-dimensional space, Lagrangian projections of Lagrangians will be one-dimensional lines sitting in a plane in this 2-dimensional space. Because if Lagrangian is sweeping the chi direction in a fiber, it has to be essentially orthogonal to one of the x directions for either omega I, omega j, or omega k, whichever is your choice. So following the same principle and asking for, again, this SO2 invariant Lagrangians, you'll end up with this 2-dimensional picture. Now it will have 2 Taub-Knut centers, and K invariant Lagrangians, or SO2 invariant Lagrangians, will be represented by one-dimensional lines sitting in this plane. Now, what we learned from Chekhanov's example of exotic torus, knotted torus in R4, is that we can wiggle this Lagrangian in any way we wish, but we cannot pass through these centers. We cannot pass through the Taub-Knut center. So this is an example of how we can wiggle and how we can do it. Now, we're ready to make identification, at least visually, with representations of SL2R. So this Lagrangian will be identified with the principal series, and it has topology of S1 cross R, those of you who know orbit method, of course, will recognize the corresponding orbit for GL2R action, which is essentially represented by this Lagrangian submanifold. And now we can ask a more general question. So let's just try to classify all possible Lagrangians. Let's try to classify all possible Lagrangians sitting in this space Y. There'll be principal series representations for indefinite Lagrangians going both ways. There'll be Lagrangians terminating at the fixed points, and there'll be even Lagrangians starting at one point and going to the other. So by looking at the spectrum of what kind of Lagrangian submanifolds you can have, you'll quickly recognize connection with classification of Saltor representations, which we had before. And picture is very visual. It's even suggestive that K-types that were running either to the left or to the right or indefinitely in both directions correspond simply to visualization of this Lagrangian. So the right way to interpret this, if you make the next step, is to Lagrangians are examples of A-branes and associated to Foucault, in a Foucault category associated to the space Y. And therefore, next question you can ask is, how about classification of A-branes in Foucault category of this symplectic space, Y, which was the tau, two-centered tau knot, or T star of CP1. So by looking at all such A-branes, you'll discover not only discrete series and principal series representations, which are easy to see in this picture, but you'll also find the complementary series. And this is the step where branes are a little bit more powerful than Lagrangian submanifolds, because the quantum, you'll be able to find something which is a little bit more quantum like a complementary series representation. So the problem that we illustrated in this simple example of Saltor is the following. We are asking for Kr invariant A-branes in the space which is complex coadjoint orbit. So the space that I took for my Saltor example was in fact coadjoint orbit, but not of a real group whose representations we wanted to classify, but rather of a complex group. So then the statement is that if you take analogous orbit for some other complex group, which is complexification of GR, and ask for Kr invariant A-branes, you'll find exactly the same classification of Harish-Chandra modules or equivalently admissible representations as you would by algebraic methods. And in this description, the analogy between geometry and algebra, geometry and representation theory, will work extremely well in a sense that, for instance, if you have a brane which consists of two components, this will correspond to reducible representation, and so on and so forth. For instance, you can have bound states of branes, as we call them in physics. This will correspond to various extensions of representations, and you can have a lot of fun playing with this game. Now, in the remaining minute, let me try to explain why does it work, or what is the underlying principle behind it. Of course, I started, in a sense, from the end of the story, and now I should tell you the beginning of the story, or how to approach it a little bit more systematically. You can start from a very different perspective, where you're trying to quantize some symplectic manifold. And thinking about the orbit method, representation can be obtained by quantization of the real coadjoint orbit. So here, if you start with a symplectic manifold M and symplectic form omega, what you want to produce typically is a Hilbert space obtained by quantization. In application to representation theory, the space H would be exactly the representation. So then the reason the previous story works is that we tried to embed in a paper with Witten this problem into a model, but not of a symplectic manifold Y, rather of its complexification. So in fact, you can reproduce the same space H by looking at the homes between two objects, one of which is a canonical coisotropic brane, and the other is Lagrangian brane, sitting inside of a bigger space, a space of twice the dimension of the original symplectic manifold, which is obtained by complexification. So that's why in our previous story, we encountered complex coadjoint orbit as a target space. And then when we were trying to classify representations of a Saltor, we essentially were looking at Lagrangian submanifolds, or in the correct language, A-branes, sitting inside this complexified target space. So here, again, BCC and B prime are particular objects in the Fukaya category of complexification, but since original data only involves symplectic manifold M, they have to be a sort of canonical, or they should be associated just to data of M without any ad hoc or additional choices. And if I had more time, I would probably describe to you how it goes. Let me just mention that this is a model, and it reproduces the story of SL2R representations that I told you in the main part of this talk. But if you want to approach it or connect it to algebraic viewpoints, you would probably take a mirror version of this and pass by mirror symmetry to a B model of the mirror symplectic manifold of the mirror of this symplectic manifold capital Y, which is complexification. And in this problem, computing this space H would be very straightforward. You would simply ask, what are the mirrors of BCC and B prime? There would be some particular sheaves, in fact, very beautiful sheaves, so-called hyperholomorphic sheaves, or BBB branes in the physics language. And computing their X groups is very easy, very beautiful, very elegant. And from this point of view, you would actually be able to produce or compute this Hilbert space H in a very straightforward manner. Mirror symmetry here would make some of the aspects of this correspondence a little bit more obscure. For example, if you go to mirror B model, computation of the space H is easy. What's not so easy is identifying, for example, answering the questions about unitarity and so on and so forth, which I mentioned in the very beginning, again, which are more visual in the A model approach because you're dealing with spaces and everything is rather explicit and geometric. Some of these questions become hidden at singularities of the space Y tilde if you go to the mirror description. So B model can be useful for one sort of questions and a little bit less illuminating for the others. So unfortunately, I won't have time to tell you about Teichmüller space and application to 3 manifolds. But since time is up, I should probably stop here.
Where does SL2R?
Yeah, SL2R is on the next slide. So let me show this. So in this, the reason you have SL2R, or rather something closely related to it, is the following. You look at complexified orbit, which is the target space. And one of the objects here is BCC, this canonical Ka-isotropic brane of a certain type. And important point is that the space of open strings between BCC and B prime, which was our Hilbert space, in order to see that it's representation, we have to show that SL2R or something like that acts on it. And obviously, what acts on this space is the space of BCC strings. In this particular example, where target is an orbit, this actually is nothing but universal enveloping algebra of SL2R.